Again, I'd like to welcome everybody to the MLC CAD Systems CAM Skills event today for why you want to choose Mastercam Mill 3D and Multiaxis. A little bit about who I am. My name is Sherman Snyder. I'm a Mastercam AE here in the Houston area. My experience, I'm going on 20 years experience now in the manufacturing industry. My experience ranges from oil field, aerospace, biomedical, and I've worked for a couple companies here in Houston, Halliburton, GE Oil and Gas, and a couple others, as well as Rolls-Royce up in Indiana for their aerospace division, working on rotatives. I got a wide range of software experience, Mastercam being the one that I am using right now that I really like. A little bit about my interests. I love traveling, which is kind of what got me up to Indiana in the first place, and back down to Houston because it's home. I love building PCs, so on my spare time, I've got a couple PCs sitting around the house, and anything new technology. So, you know, when you're on Facebook and you see something that pops up that you mentioned in a conversation with somebody else, that kind of stuff usually catches my eye and takes me down some kind of wormhole. At the end of the day, I'm a family guy, and got 4 kids, a very patient wife, and I'm also happy to be part of the MLC CAD family family here. So again, I'd like to welcome all y'all to our CAM Skills event again. And let's go ahead and take a look at our part that we have here. We have one side of a basic mold assembly that we're going to be looking at today. So without further ado, let's go ahead and get started. So first thing I want to talk about inside of Mastercam here, we're going to mention software designed for optimum productivity. And when I think of trying to optimize productivity inside of Mastercam, the first thing that comes to mind is one of the simplest things that come with the very basic package, and that's view sheets. Now, we're talking about 3D Mill and Multiaxis, but the reason I bring up view sheets is because it optimizes the ability to change your planes, levels, and any kind of other views that you want to have within Mastercam. So typically, if you're working multiple sides of a part, instead of going through your managers over and over, you can simply go through your view sheets. And if you haven't seen the view sheets before, at the bottom of our graphic window, let me move this over, you can see the view sheets tab at the bottom for each one of my view sheets that I have. And under our views tab at the top, under view sheet group, you can toggle this off and on. So if you're not aware of that, that's where you'll find your view sheets here. So whenever you create a view sheet, you notice there's a bookmark for each one of these view sheets that I have. And this bookmark signifies the difference between one view sheet and another, and it's been saved under that view sheet, whatever my settings were. So let's take a look at, let's say, our planes manager here. And you'll notice that I am set up in the top plane. You can see the WCS displayed. And you can see what happens when I change to my operation 2. My part's going to flip around, and it's sitting in the vise properly for operation 2. But you also notice my top plane is flipped around, and we can display this plane. And let's display the top plane as well so we can see the difference between the two. So within Mastercam, just by simply switching the view sheets, once they're bookmarked, I can change settings. And what you'll also notice, if I go to my levels, we have the ability to suppress geometry, just as you see here. I could turn geometry off and on. So what this allows me to do is inside of my Toolpaths manager, whenever I'm creating toolpaths, I can simply toggle between each one of these settings here and pick up the planes. So this works, it comes in very handy whenever you're working in multi-axis or simple 3+2 operations where you want to go from one phase to the next. Once you save your settings, you don't have to go back and forth between all your plane managers and your levels managers trying to suppress geometry and then back to your tool Toolpath Manager as well. So it increases your workflow here and basically keeps you looking at your Toolpath Manager and your graphics window alone. Now what we have here is just a simple face pass. I use a dynamic face pass for this just because it looks a little more interesting. Let's go ahead and look at what's next on our agenda here. So next on the agenda, we have intelligent part and stock awareness for toolpaths. And whenever I think of any kind of stock awareness, the first thing that comes to mind is OptiRough operations and OptiRest. What OptiRough does is it increases the efficiency of your tool by allowing you to take larger steps with using the intelligent dynamic motion within Mastercam. So instead of taking 100 thou at a time to get the nice steps that we see here down the part, we could take them in larger strides, say a ½ inch at a time, and then step up a 100 thou each time. And doing so, you're using more of the blade of your end mill instead of just burning up the tip little by little. But what OptiRough and OptiRest also allows you to do is take advantage of reading the solid. So in a sense, looking at the regular toolpath that I would have using my 2D toolpaths for a contour, you can use a 2D dynamic as well, but I'm only allowed, whether I'm using contour or dynamic, to cut the profile of this part. Afterwards, you would have to most likely create a ton of geometry in order to get this shape out. Now, the reason I have this toolpath here is because I also want to compare, as simple as this path looks compared to how crazy this one looks, I want to compare time. And inside of this file for Mastercam, I've put all my feed rates at the same, so as we go between one operation to the next comparing time, we can get a more accurate time and see what's going on and how Mastercam is working with the OptiRough and, in this case, contour. So if I backplot this operation, and let's go ahead and drop this down and look at the information here. So for this basic contour toolpath, I'm running close to 29 minutes. And this is just cutting the profile. So if I go look at my OptiRough, and I want to take a look at some of these parameters while I'm here as well, you can see that I'm stepping down a ½ inch at a time, but I'm only stepping over about 10% of my tool. And what we're taking advantage of here is the ability to run faster feed rates. So we have a radial chip thinning here, and you'll notice my feed rate kind of changes a little bit here. So it's taking advantage of the radius of the tool itself on how much it's engaging into the material. But back to our cut parameters. After we're done stepping down a ½ inch at a time, we're going to begin stepping up 100 thou to take care of the little scallops that we want to leave for our finishing. And what this is doing, if I look at my contour, I'm actually having to cut all my material from the outside, stepping down. Whereas if I regenerate my OptiRough, we're stepping down a ½ inch and then working our way up to the middle or to wherever our part material is, avoiding having to cut from the outside in every single time. And at the same time, we're reading our solid. So that's the advantages of using the 3D OptiRough for our 3D mill package. So next, I'm going to go ahead and generate a stock model. And one thing I want to point out inside of our parameters, when you do create a stock model, new in 2021, they actually introduced a naming convention here, 1, 2, 3 for each stock model. So if you tend just to skip past the name, they've put an option in there just to automatically name it something for you. But under our source operations, you can see I have a couple toolpaths already chosen. And what I want you to see is I also have a toolpath that's not chosen. So you could select multiple operations And you can also skip operations that you don't want to use for your stock model. Now, for this compare that I created, it was just for that. I want to go ahead and ghost this toolpath out. That way, when we work later on down the road, we're not going to see it. So next up, I also want to talk about OptiRest. And what OptiRest does is it takes advantage of the stock conditions from either previous toolpaths, or in this case, I said one operation, and I gave it the ability to read my stock model here from the first two paths. I'll say OK to this. I'm going to go ahead and regenerate. And what we see here, being that I'm using a smaller end mill to get into this little cavity here, Mastercam is recognizing the material that's left behind. And I see we have toolpaths up top as well. I'm going to go to my parameters. And you'll notice that I still have the 1/2 inch, but I've changed my step up to 50 thou. So now every 50 thou where it's going to hit material and fall between the 100 thou steps from the OptiRough, it's going to make an additional cut. So let's go ahead and move on to our next agenda here. We're going to talk about advanced multi-axis tools for 3, 4, and 5-axis work as well. And whenever I think of that, first thing that comes to mind is surface milling. And inside of surface milling, we have, we could start with the simplest surface milling available under the 2D package. We have 2D sweep, we have 3D sweep. Then we jump into the 3D toolpaths for Mastercam Mill, where we get into more complex surfaces and the abilities to utilize what we have for UV and flow UV. So inside of Mastercam, let's go ahead and take a look at that. And as we walk through this event here, I want you to notice that I'm taking advantage of my view sheets at the bottom. And if you simply look at the naming conventions I have, it pretty much follows what we have for each one of these topics that we're going to be discussing today. After all this is done, if anybody has any questions or wants to see a copy of the part, just I'll put my information out there, and you can kind of follow along with what we go over today. So the first thing I want to talk about, though, when it comes to surface milling, we're going to look at the simple 2D example here. And you'll notice when I look at my geometry, nothing is truly driven from the surface. It's actually driven from a line and 2 other lines that create the curve that we need to follow. That being said, whenever we create any kind of surfaces, in this case, we're going to look at these parameters, and you'll notice that we have a lot of things missing out of here that we can absolutely take advantage of on the 3D side. And I'll show y'all here in a minute once we get there. But what I want y'all to see is we have along and across curves for the direction. And we do have an array of cutting methods here. We can still comp the tool. And even if I close this out here and let's tilt at an angle, you can see how the tool does follow the radius of this ball mill that we're using. And it does step away from this curve. Now, the problem is what happens when we get to a curve like this here, a multiple surface? Or in this case, let's take a look at this front. And even though I'm using 3D for this here, this is a 3-axis toolpath. But you'll notice on the parameters, we have a little bit more options available for us. I can give it clearance, I can give it direction, which is a main thing on how you want to engage into the surface. We also have the ability to talk about distance and scallop height, where the 2D toolpath wants to follow just a distance there. And another key factor inside of the 3D flow line here is we have the ability to arc filter settings. For now, I'm going to leave those as default. And I'm also going to go back to my surface parameters here. I'm going to talk about another option. So if I show the geometry that we're using, and I've created these basic curves just to simplify the part, give a better view so it's a little more understandable. We're going to take a look at this one curve here. So this surface is the single drive surface that we have, but now we also have a check surface. And if I look at the toolpath, using the 2D function, my toolpath would extend out and possibly allow the tool to collide to this floor. Where for my 3D flow line, my 3D surface parameters, I have the ability to give it a check surface. By selecting the surface, I could say OK, and I could tell it how far I want that tool to stay off of this material. So let me go ahead and regenerate this again. And we're going to take a look at a couple more advanced features for surface milling capabilities within Mastercam. Now you notice no matter how I flip this thing around, I can always go back to my view sheet, double click on it, and it will take it back to the original bookmark setting that we have. So moving forward, we're going to talk about accelerated form tools here. And one thing I'd like to mention before we move along is you notice in the last toolpath I talked about for the 3D flow line, so we had the ability to have the step over be a certain distance or a scallop height. So if you're not too big into surface milling, you might be asking what a scallop height is. And the first thing we're going to talk about here for our scallop height, your scallop height is going to be the material that's left behind. And it's going to be a combination of your tool radius and your step over distance. Now, you'll notice that in this case, I'm using a ball mill. And we're going to jump into some more advanced tool geometries here. And we're going to talk about using tools such as a oval form tool. We also have lens form tools as well, barrel form tools, and taper form tools that you see here. If you're not familiar with barrel shaped tools, they use a portion of the circumference here to allow for a larger cutting radius to make more contact with the material. This is going to greatly reduce your machine time. It's also going to give you a better finish. And when we go to our Mastercam file, we're going to start with our accelerated finish here. And we got quite a few examples that I can show you that have, in this case, we'll start with the oval form tool that we have. And I basically put this toolpath on here so you could see, get a really good visual of what we have for the contact of this tool being made. So if I play this a little bit, and we'll just speed it up until about right there. Let's step back. So if I was running a ball mill on this, the only contact I'm making is with the very tip of this tool. And theoretically, running the tip of the tool is pretty much at a 0 RPM point, being right in the center. So in this case, we would probably still tilt the tool to stay off the center. Now, what you notice about the form tool is no matter on a radius of a ball mill, I'm always going to be running on a point. In this case, we start running a larger radius. So even if I have a 1/2 inch diameter ball mill versus a 1/2 inch diameter oval form tool, I can say that instead of having a certain size radius, I can give it maybe a 3/4 radius on the side. So it's not driven by the diameter of that tool. Now what we'll see here is I actually have an example of a form tool for a barrel form tool. And this surface was a little bit less than about 1 inch. So I actually created a surface that was about 3 inches long here. And the reason I done this is because I wanted you as the customers here to understand what kind of time frame you're actually saving just over a 3-inch toolpath. So if I look at it as the front here, and you notice we have a larger step over than we did. My parameters are set a little bit different for this barrel form tool. So we're going to look at the cut pattern that we have. And inside of this cut pattern, you see that I have a scallop height of 1/10. And I could go far greater on this, but even with 1/10, I'm stepping over every 140 thousandths basically. We can see our tool axis here on this output. All the accelerated finish toolpaths will be under multi-axis, but you do have the option to run 3, 4, and 5 axis. For this one, we're going to run a 5-axis surface with a tilt. And I'm just going to say OK to this. And let's run this toolpath. So we'll step down. And you see we have a larger radius on this one here. It's a little bit more defined. We can step back. And you see how much of that radius is touching. So by the time we get to this side here on the next toolpath, we'll have that 1/10 of a scallop height that we defined within our settings. Now say we don't want to tilt and we actually want to come from the face. Maybe we want to be able to control how much our tool tilts if we're over our fixture. We can also take advantage of using lens form tools as well. So in this case, we'll look at the cut parameters here, and we can take a look at this scallop height. I have 5/10 for this lens tool. And we can also control this by our tilt angle that we want to have, which I gave it -2 degrees from being parallel to this face. So we're just slightly off the center, which is why we have such a smaller step over. But let's take a look at this tool on how it's going to react as well. And we'll stop it about right here and step back. Oh, it's not all the way. Right there. There we go. And we can zoom in. And we can see how much that radius of this lens tool is touching the part as well. So even if you don't want to use a barrel form, you also have the option for lens if you're running in a 3-axis setting and you don't want to take a ball mill and actually run over a parallel surface. Now, I want to compare the time that it takes for a ball mill. And right off the bat, we are using a multi-axis toolpath here. And I can kind of explain how this toolpath does work. We have the ability to read 2 curves here. Notice I have the top and bottom selected. And we also have our drive surface, which is just that one surface that we have created. And of course, I have my settings in place here. But what you'll notice is I have 5/10 scallop height here. I did set my output format for 3 axes. So again, you do have the ability to take advantage of these multi-axis surface operations to be in 3, 4, and 5 axis output formats. Now, when it comes to the multi-axis toolpaths, you also have more options for collision control. And in this case, I'm just using my drive surfaces. But I can also tell it that we have check surfaces that read off my shank and my tool holder as well. We can define how we want this toolpath to work. I can say I want to trim and rethink the toolpath. If I have my multi-axis settings, I can say I want to tilt my tool around something. So that's the advantages that come with the multi-axis toolpath. Now, you also have additional controls here. and roughing options as well for surface milling. So for now, I just want to go ahead and compare the time. And what we saw there was in this toolpath, I had a 5/10 step over. And if I backplot this toolpath here, we can go to our information. And it's going to take slightly over 3 minutes here to be able to machine this whole surface with a 5/10 scallop height. Now, if we look at the, say, the barrel form, which we've seen inside the parameters, and we'll double check, we have 1/10 scallop height. We can go ahead and backplot this here. And you notice that we went from 3 minutes down to 41 seconds. We'll call it 42. So it's basically taken about a little over 2 minutes off of the part just from what we have from a standard ball mill to our barrel form tools. So this is the advantages of using the accelerated finish driving with circle segments within Mastercam. Now, just as I said before, we could run the ball mill under a 3-axis toolpath. And I want to show this in a 4-axis as well. And you notice here we have surface with a tilt. I could even tilt, say, along 15 degrees, just to give it something we can see. And now as this tool flows around the part, let me minimize this real quick. We can see the 4-axis motion happening on this particular machine. So even if you're using a VMC with a rotary, you could still take advantage of the multi-axis toolpaths as well, just by defining what you need to do inside of your parameters here on how you want to tilt. Now, the next toolpath I have, this is a Multiaxis Morph. And under my view sheet for Multiaxis Morph, you'll see I just have the sheet pulled off of the model here. And the reason, again, I've done this so you can get a better visual of what we have. But we could actually run right off of the model as well, which you'll see next. Inside of this toolpath, we're going to take a look at a couple of the features that we have to be able to contain our tools and how we drive our tools as well. So just as we've seen before, I have 2 curves, and you'll notice I have a pattern from curve at the top, and I have a pattern to curve at the bottom here. And then afterwards, I have my drive settings, which is just the basic sheet that we have. I'm going to put it back in isometric. We'll say OK. And next, I'm going to look at my tool axis control. Now, I still have all the options using my morph toolpath here. I'm going to keep this at 5 axis. And I'm going to tell it I want to tilt angle from point towards axis. So I select my from point, which we see here. And under my collision control, I take advantage of using my check surfaces for my model so that my holder doesn't collide with the actual part itself. So if I generate this toolpath, and just by using this basic sheet here, let's go ahead and turn the model on actually. There we go. We can see how this tool flows using that pivot point that we've created. Very simple toolpath, not a lot of geometry to select, and that's the reason why I display just like this with this simple sheet. When it comes to Mastercam multi-axis toolpaths, what I tell people most of the time is what you get right off of the actual settings, as far as once you select your geometry, if you regenerate it, most of the time you'll have something pretty close to exactly what you want. Then it's just some fine tweaking on how you want to tilt your tools around. What I want to show you next is how we can utilize our morph toolpath again under a 4-axis operation. And what you'll notice is I have a couple curves that I've created here just to kind of define the area that I'm working with. And I also have a line entity sticking out at a 45-degree away from this curve. Let's look at the parameters that we have here. And you'll notice right off the bat, my output format was set for 4-axis. And this time I'm using a tool axis control of lines. Now you'll notice under here, I do have other options. I can surface. I could follow a surface with a tilt angle, angled towards tilt axis, fix angle to axis, rotate around an axis, and you see my point options, chain options, and the line that I have selected. So if we take a look at this line, my tool is going to take advantage of that multi-axis toolpath in a 4-axis motion, keeping the tool at a 45-degree. Again, we also have our collision control, any kind of gouge settings. And if we look at our linking parameters, we also have an array of linking parameters in here that make the toolpaths for multi-axis more in-depth compared to what the 3D settings had for their surface milling. And again, we also have the ability to rough this surface in multiple depths and multiple passes as well, if we want to come in from the side. For now, we're just going to look at the actual toolpath itself. We'll backplot this toolpath. And we'll continue on here. And on this one, being that the machine we're on, it's not going to follow that 45-degree there, so we'll have to tilt that at a 5-axis here in a minute. So there's our morph toolpath using a 4-axis machine. This machine is a Haas UMC 750, so it does matter how this part is set up on how it's going to tilt for your 4-axis. If we put it in the 5-axis here, let me see, axis control, 5-axis, and let's get that nice tilt that we want. There we go. Now, what I want to display when you do follow your line like this, on the point, we actually pivoted around that pivot point there, whereas when we drive it to a line, this tool will stay stationary. So in this case, you still will have a 4-axis operation, just with the way this machine tilts. We would actually have to have the part running this way, almost like we were reading an A-axis to flip around. Now, with all the toolpaths that we have on our part, the next thing I want to talk about is how Mastercam can be a solution for complex parts and setups. And when I think about a solution for complex parts, the main thing that comes to mind for me is machine simulation. And Mastercam machine simulation is a safe and it's a cost-effective way of proving out 3, 4, and 5-axis mill or router toolpaths, actually. Machine simulation helps with the detection of any kind of collision from your stock to your tool, and most of all, your machine components. It's a lot cheaper to break a tool than it is to break a spindle on a machine. So this is the reason why Mastercam has the ability to simulate any kind of toolpaths that we have on actual machines for the simulation. So I'm going to go through and minimize some of these toolpaths here. We can keep our OptiRough operations, and we can remove some unnecessary toolpaths that we don't need, like these. We can ghost those out. We'll keep the morph, and we'll keep that simple morph on the end as well. From here, I'm going to put it in the view sheet for operation 1. We're going to take a look at our nice fixture here. We got a vise from 5-axis. And you'll notice that I'm going to run the simulation here. And we'll let our part load. There we go. Now inside of Mastercam, you see that I have that one operation. My part is tilted. I'm trying to get in a nice orientation here. But all we have in here is our table and our housing for our spindle here. We also have the ability to have the complete machine, just in case you want to stand on the outside, push buttons. For now, I want to see just the head of the spindle and my material. And actually, let's load every single tool path that we have here. We'll go ahead and run the simulation. That way we can see it from the very beginning, see if there's any collisions that we have. All right. So you'll notice some of these toolpaths that we have, it's going to be pretty much 3-axis. Again, this is a Haas UMC 750, so you see the trunnion and the C-axis here. We'll go ahead and run this toolpath, and I have my dynamic face milling being done. We'll slow that down a little bit. So here's the example of our OptiRough operation, and again, it's just reading the solid that we have. You see the large step downs with my 10% step over. And then it steps up 100 thou to take care of the profile of the part here. And from here, we have our OptiRest operation for rest material parameters. And it's stepping down every 50 thou to give it a better step over whenever we come in for surface milling, so we don't have so many tall scallops. And again, you see that large step down. And just as you've seen on these peaks for our die mode component here, it's going to end up stepping up every 50 thou as well to get that nice valley that we have here in the middle. And after we're done with the simulation, I want to go back and I want to time compare this with both operations for OptiRough and OptiRest as well. So we'll go ahead and move forward with our toolpaths. And I want to point out why the simulation for Mastercam is important whenever you're doing multi-axis toolpaths. So right here, we can already see the tilt angles of my tools. And we have the ability to see if they're colliding with our material here. But notice what side this tool is on when it's surface milling this middle surface here. And once we get to about the center of this table, I want you all to pay attention to what happens. Now, the table is flipped around, and Mastercam is starting to force the tool up the left side, which it just came down the left side going right. So this is the reason why using the simulation could help with any kind of collision, but you can also see what your tool's actually doing. Where if I verify this toolpath, let's go ahead and step back. We'll say that was our morph here in the middle. If I just backplot this or I verify it, it doesn't matter. What we're going to see is the tool just following the part like this. We don't see the actual table flipping around 180 degrees once it gets to the center. So if you are looking at the multi-axis side for a full 5-axis machine, simulation may be something that you want to take a look at. And even on the 4-axis side, if you want to see that full machine simulation, that's the importance. You'll be able to see any kind of collision that you have on your part and get a real world view of what you're actually seeing. Now, as promised, last but not least, I do want to go back. And before, I only showed the time comparison between OptiRough and our compare for our contour. Just running that simulation there, I was a little curious of what the OptiRough and OptiRest would be versus our contour as well. So go ahead and back plot. We'll look at this time here for both operations. And even with both operations, I have about 17 minutes, 17 seconds plus 14 minutes. So we're at 14 and a half minutes here. And with my contour, I'll take a look at this as well. Got to unghost that real quick. There we go. And it's 29 minutes. So we're still getting over a 10 minutes there for saving and still being able to drive more of this profile of this part. So I will have this part available if anybody wants to send me an email. I'll put my information here in the chat. And I'll go ahead and open the floor for any kind of questions. Thank you, everyone.